Okay, so we are continue to look at string matching. So earlier we look at string matching using PDA. So we construct a PDA. I'm sorry, not PDA. We use a DFA, right? Deterministic finite automata. We construct a deterministic finite automata for the given pattern. So then, to find out all the occurrences of that pattern in a given string, we just need to run the string on that finite automaton. Then we can do it in linear time. So the only thing that is not ideal is that the pre-processing time of constructing a finite automaton takes m times sigma. So the size of sigma is the number of symbols time. Okay. So then KMP algorithm provides an efficient implementation of the DFA approach without actually constructing a finite automaton. Okay, so these all looks involved. So I just need to show you an example, then you'll get the idea pretty easily. So actually, it's not hard. It's just the description here looks imitating. Okay, so the idea then is that we have. So let me open up a blackboard here, whiteboard. Okay, so we are going to have our input string. They call it T. And we have our pattern. Okay, so of course we obviously want to match to see whether these two are the same, but then we recognize the fact that even though P is not matched with this portion of T, there may be partial match. So in other words, for instance, we were able to match until this point. Okay, so then if this part is matched, so in other words, this part and that part is matched, then when you see this is not matched, of course, then the naive approach will start from here and match it again. And finite automaton approach says that you don't have to start from here. Instead, what you need to do is to look at this prefix of P, okay, to see whether there is a prefix of this prefix of P that is actually the suffix here. Okay, so now the only twist is here. So we look at the prefix of P because that is a partial match. And then, and this is not matched. So instead of starting in this position, I just need to find a correct position where I can begin with my match comparison or matching. So in other words, what I'm going to do now is I'm going to say maybe this portion, and so this is a prefix of the prefix of P, okay? So that's the only twist, okay? And then if this guy here is the same as this guy, then I can just start from matching from this location instead of starting from here. And we don't need to construct a DFA. So that's it. So that's KMP algorithm, basically, okay? And so let's look at an example. Let's go back. Let's go back. All right. So first, so let's say we have a P here. So first we're going to look at all the prefixes of P, and within each prefix, so within each prefix, I also compute whether there is a prefix that is the same as the suffix. And of course, we want that to be the largest possible. So that determines when my partial match cannot continue, my next matching position. So that's KMP. So that's the core idea of KMP. Okay, so that means now we first compute this thing. And so let me just use an example to look at KMP, then we come back to this. So I think I have a example here. Now, don't worry about this code. Once you understand the algorithm, this becomes straightforward. All right, so this is the algorithm. I'm sorry, the example. Okay, sometimes, okay, sometimes, all right. So this is my T, and this is my P. Okay, don't worry about the other part. So I'm just going to start from here. So we start, so I guess A and A is matched, and B is matched, A and A matched, C and C match, and A match. But now this is not matched. So that means now I have, so this is the prefix of P that it's matched. So that means I have A, B, A, C, A. So from here, I want to know whether there is a prefix here that's also a suffix. Of course, we can see here, this is A, this is A. Okay, so that is the position. I can simply move the whole thing from, so this is the position that it's matched with the prefix. So that means now I can move the whole pattern to this location. So that's where I start. So this is where I start. Okay, so then I do the same thing again. So A and A, of course, we know that's matched. So we don't even need to make that comparison because we know they are matched. So then the next one here is A. This is A. And this is B. So that is not matched. So the prefix now is A. Okay, so of course, so because this is A, and you cannot be, so in other words, when we look at so when we look at the prefix of P, what we are looking at here is that something which is not entire substring of this portion, but a substring of it that is the same as this. But here, of course, you cannot have it. So that means that the matching position is 0. So that means now I start from here. So it's matching. I'm going to start this A to point to this particular location. Okay, so then I compared it again. So A and A here. So this A is matched. B and B here are matched. A and A are matched. C and C are matched. Now C and A is not matched. Okay, so now then I'm going to say A, B, A, C is the partial matched, and then we want to see whether there is a prefix that's also suffix. Then we don't have it, so it's a 0. So 0 means that at this location, that the one that is not matched, I'm going to put the new string here because that's where I'm going to start. You cannot put any. So if you put these things earlier, it's no use, right? Because you know they're not going to match. So we start from here. So we do it again now. A and
Professor,
C.
I had a
Yeah.
question here.
Yeah.
So since the prefix, like since it's 0, since the precision is 0, shouldn't we just go to the next like letter instead? Why do we even bother with number 13?
Number
So
here.
if we know that the prefix and suffix don't match. So there is no way that C is going to be the beginning. So then we should just move on to the next one, right?
Oh, because we don't consider this C when we look at this pattern. So you could, the next one, it could be matching. Okay, it could be A here. You see what I'm saying?
Yeah.
Because what you're trying to see here is that.
No, I got it. I got confused because the C's are like there are two C's one after the other. So I got confused with the prefix and the next letter. We are actually taking the next letter. I just got confused.
Right. Just taking the next letter. Yeah. Okay. So we are going to move. So it's not, again, it's not, so it's not matched. So that means that I will just move to the, so we just move the next one. Not match means that the length of that prefix and the suffix, that's length is 0. So that means that I'm just going to move over here instead of move a lot. And then I compare. So this time is A and A, B and B, A and A, C and C, A and A, B and B. So that is matched. Okay, so then the next thing, okay, so where do we start for the next one? So it's just a match. Then we are going to do A, B, A, C, A, B. So here we got A, B. That's a prefix. That's the same as suffix. So that means the next thing you can do is I'm going to move from, sorry, here. So right here. So I'm going to move A, B. Let me erase this. Okay. So next one is going to be here. A, B, A, B, A, C, A. Okay. So basically that's the algorithm. So then we want to know the running time. Okay, so the running time here, so let me start a new. A whiteboard. Okay. Maybe we should see that. Okay, so running time, we have two things. One is to compute this pi value. So there's a 1, 2, let's say up to m. Okay, how do we compute pi of q? So these are the index q. Okay, So of course we know, so it just means that when I have Q here, I want to know this portion, whether that portion and that portion are the same. So that we just need to look at the previous K. Let's look at the pseudocode. The code is in the slide. Yeah, so this computes a prefix. All right, so now let's show the idea here. How do we compute it in linear time, right? So the naive approach would be for any Q, say this is M, so this is Q. A naive approach just means that, okay, I'm going to start from here, and then you're going to start from here to see whether this and that's equal. If it is, I move on to the next one. Let's see whether they are equal, right? So, but then for each time, for each Q, you're going to run about, in the worst case, a Q step. So that is quadratic time, but we want linear time. So the idea then is, the linear time is that when you have a Q, you're going to take the previous matching. So for instance, this is my Q, and the previous one is here. So you already compute whether this guy is the same as this guy. So what I need to do now here is that I want to know whether this guy is the same as that guy. If that is the case, then I know my new, so this will be the new string that matches this. So using the previous matched information, so that way it's so it saves time. Okay, so then that's what it is. So if it's not, so this is the case one, so it's an equal. If it's not equal, maybe I draw a bigger one here. Draw a bigger, so you can see it better. So case one. Okay, so this is my partial. So this is a Q. Okay, and this is M here. So I want to use the previous information. So previously, now in this part, I have already computed a value here that is the same as this. Okay, so this part is the same. So now to determine, so pi of Q, so what I need to compare now is compare this guy and this guy. Okay, so if this two, so this and that is equal, then I know pi of Q is the previous one. Say let's say that's K. Then that's just K plus 1. So that's case 1. So then, of course, the case 2 says, now this is the previous one, this is equal. But this guy is not equal. This is still Q. Now, what do I do? So then what I'm hoping is that I'm going to look at the new, so the so when it's not equal, so that means I'm going to look at a I'm going to look at here. So this thing is equal to this thing. So now I'm going to see that here is that whether this guy, now this has something here, and this has something here. Now I'm going to see whether this thing would be the same as this thing. Okay, so that way I can compute this pi of q. All right, so this is step here. So if it's not equal, I keep shrinking. Okay, so keep shrinking this k. Until it's equal, then I'm going to, until it's equal, then I'm going to come. So this is the same, then I increase the k. So that is how we compute this prefix. All right, so y is a linear time. So y is a linear time. Okay, so first you look at how many times I can increase this value k. Okay, so the increase altogether, right? So your q starts from 2 to m. So the number of times you can increase this k is at most m. So this is at most m. But then you also have a decrease. K could also be decreased from this step. Okay, so, but it can never be negative. So now that's important. It cannot be negative. So that means that you can increase at most m times and each time by 1, right? So which means that the increasing portion is only this much. So the decreasing, now each time you decrease and you increase back, so you have m times increasing. So this is m times, at most m times. So that means you are decreasing, you decrease it and later on you will increase it. And then you decrease and later on you increase. You count the total number of increasing, that's m. So the total number of decreasing cannot be more than m. Okay, so basically that is the most, that's the important part you see. So you can increase at most m times. You can also decrease, but you decrease later on, you also increase, and then maybe you decrease again, but you also increase. But the total number of increasing is m each time by 1. So that means that the total number of decreasing cannot be more than m. Okay, so hence it's just linear time. Okay, so the number of operations of increasing and decreasing is at most 2 times m. So that is linear time algorithm. All right. And the matching algorithm also the same. Oops, cannot erase it. All right, now it worked. Okay, so basically this is linear time. So why is it linear time? Again, we look at the number of increasing is at most n. because it's from I from 1 to n. So this is increasing. Okay, and you also, Q could also be decreased. So once again, increasing is at most n times. Each time is by 1, right? So increase by 1. And decreasing, each time maybe decrease more than 1, but the total number of decreasing cannot be more than the number of increasing. So again, that's the n increasing operations and n decreasing operations. So this is a linear time. Okay. So that's it. So that's KMP algorithm. It's not hard. It just, it has a very clever observation on this partial matching. Okay, so you figure out partial matching, where would be the next position you start matching again. So that means that for the partial matched string, if the next one is not matched, so then you calculate the prefix of the partial matched, which is also a prefix of the pattern. The prefix of P, that is a suffix. That is the location. So the whole suffix, okay, would be where you put your new pattern. You move your pattern to that substring, the suffix part. Okay, so that is string matching. Any question? Okay, then let's look at a new topic. So now again, we're gonna switch our mindset to a new topic. What's going on here? Do you see the screen?
Yes.
Yep.
Okay, all right, good. All right, so we're gonna look at a new topic, which is not here. Okay. I'm going to okay. Trying to get a whole full screen. How do I do this? Get rid of this. Okay. So we're gonna look at intractabilities. Okay, so let's look at this general slide here. So the study of algorithms typically follows two directions. One, of course, that is what we have been doing, seek more efficient algorithms, right? So We know there are quadratic time algorithms, and it's pretty easy to design. And then we try to push our limit to reduce that quadratic time to linear time. Okay, so we have seen two algorithms in this direction, design in this direction. So one is the multiplication of two polynomials. Naive approach is n square, and then using fast Fourier transform, we can reduce that quadratic time to almost linear. That's n log n time. String matching is the same. So naive matching algorithm, which everybody can do, is simply quadratic time. And then we try to push our limit to reduce that quadratic time to linear, but of course, we can push that to almost linear. That's n log n time. I'm sorry, that is actually linear, but with pre-processing. Okay, some pre-processing, and the pre-processing for KMP algorithm is also linear because so then the whole thing is a linear time algorithm. So that we were actually for string matching, we are actually able to push quadratic time to linear time. So there has been almost everything that we have tried to do in algorithm design course until now. Okay, so then we need to look at another important topic, which is the following. So it turns out that this effort in the first direction may not always succeed, may not always be successful, because there are quite a number of problems, actually thousands, optimization problems in practice, that no matter how hard people have tried, they are not able to find efficient algorithms. By efficient means they are not able to find polynomial time algorithms. So then people wonder whether we are not smart enough. Okay, so all these people before us, they were just not smart enough to come up with polynomial time algorithms to solve these problems, or there's another much more deeper reason. That means that these problems are perhaps intractable. So they are just not, you cannot find polynomial time algorithms. But either way, we still do not know the answer to this at this time. So are we smart enough, or are these problems just don't have efficient algorithms? We don't know. Okay, so that is a P versus NP problem. But then we still have a big body of studies about these problems. So people then figured out, they identify the hardest problems in such types of problems. So if we can solve one of those, then all these difficult to solve problems become solvable. In other words, all these problems that don't seem to have polynomial time algorithm, as long as we come up with a polynomial time algorithm for one of those, then all of the others will have polynomial time algorithms. Or if we can show one of those which cannot be solvable in polynomial time, then all the others cannot be solved in polynomial time. Okay, so that's what we're going to address in this lecture. Okay, so we're going to deal with the second direction. So first, some concepts. So it is customary to view polynomial time algorithms as efficient, even though sometimes we don't think, or we don't view a polynomial time algorithms with high degree polynomials as efficient. For instance, if you have n to the median, where n is your input size, obviously in practice it is no way near efficient. But if you look at asymptotically, so it is still much less than exponential. Okay, so when n goes to very big, so it is still much less than. Because even though this is big, but no matter how big it is, no matter how big this k is, it is a small o of 2 to the n. So that's one reason that we view polynomial time algorithms as efficient. The other reason that we work on polynomial time is that in practice, I'm sorry, so the other reason is that polynomials have good mathematical properties. Okay, so in other words, I think I have a slide. And then move to the next slide here. So let's look at, so we just mentioned number one. So the second properties is that polynomials are closed under addition. So you have two polynomials, you add them up, it's a polynomial. So that is a good measure, right? So it is a good measure. And then if you have two polynomials, you multiply them, so the result is still a polynomial. So that means that this measure is closed under addition and multiplication. And if you have a polynomial p of x and q of x, you compose them, you still get a polynomial, so which is good. So because then you can combine several polynomial time algorithms together, you still end up with a polynomial time algorithm. You don't get an exponential time, right? So this is good. And there is one more reason, which I didn't put it on the slides, is that remember when we study computation, so we usually use a Turing machine as our computation model, single tape Turing machine. But of course, that is not the only model out there. There are other models, such as Turing machines with 2 tapes or K tapes or 2-dimensional tapes, or even we have some other computation models that don't involve Turing machines, such as lambda calculus. So they are just like calculus, but it's a computation model. It turns out that all of these computation models are equivalent to Turing machines with a single tape within a polynomial time bound. So in other words, if you have a problem that's solvable with a different computation model in t time, then your algorithm, you can convert that algorithm to a Turing machine on single tape in p of t time, and p here is a polynomial. So that means that these computation powers are equivalent between different devices within polynomials. Okay, so that's another reason. So that's sometimes called extended Church-Turing thesis. All right. But nevertheless, we just want to establish the fact that using polynomial as time measure makes a lot of sense. Okay, so from now on, then we are not going to argue with that point. All right. Okay, so let's see what is here. So then the question here is, how do we know if a problem cannot be solved by a polynomial time algorithm? Okay. So then this is the question that we want to answer. To do that, again, we need to use a computation model, and that is Turing machine. So now we're going to look at Turing machines. Now, when we study algorithms, the underlying model we have is called random access machines, or RAM. So this is not random access memory. Instead, it is just a machine plus a random access memory, right? So it's a CPU plus RAM, which can be programmable using pseudocode. So we didn't mention it explicitly, but this is what we have been using. So we assume we have a computation model which has a CPU plus a random access memory, and hence it's programmable. The pseudocode can be used to program this random access machine. So that's what we have been using. So for study intractability, we want the most basic computation model. Okay, so this is not basic because it has this random access memory. So what is the basic? So basic would be I have a finite control plus a single tape memory. And that's what we call the single tape Turing machine. So that's what we're going to use. Okay, so then the time that machine takes would be the number of steps it involves in computation. So now let's look at this part. So we use time-bounded, deterministic, and non-deterministic Turing machines to study computational complexity of decision problems. Okay, so this is the first thing. So we use Turing machines. Okay. Now, in this model, a Turing machine has two different halting states. One is called the accept state. The other one is called the reject state, or accepting state or rejecting state. So this is called the time-bounded computation. So that means that if you have a time-bounded, you run this Turing machine on an input, it will always halt. Okay. Once this time is exceeded, then you stop. When you stop, if you end up with accept state, you accept the string, otherwise you reject it. So that means we can put a measure on the number of steps to it. So then we say that this Turing machine M is bounded by time t if for any input x, M on x always halts in t of length of x steps. Okay, so this is the size of your input. Moves means the transition is a finite control. Right? So it's a finite control. That's the from one state on one symbol, you move to the next state, and then you change the tape symbol. You either move left or move to right on the tape. Okay, so basically, one of those is one move. Okay, so what's a deterministic and non-deterministic? So deterministic just means that you always have a unique next move. Non-deterministic means that from current situation or from current configurations, you have more than one choice to go to the next configurations. Okay, so that is non-deterministic. So the only difference between deterministic and non-deterministic is the acceptance notion. So for the non-deterministic machine, you can think of the computation as a tree. So let me start a new. poor here. Okay, so let's say I have the initial, so this is a non-deterministic Turing machine. So this is one tape. So this is the simplest computation model, and it's equivalent to any computation model that there are. So well, I shouldn't say there are. There have been devised within polynomial time bound. Okay, so so then you start from your initial configuration, so which is Q0x. So deterministic, you only have a linear step, okay? And then you stop. So this is DTM, and this, you have, so the length of it is T of length of X. Now for NTM, you start from your initial configuration. X is input, Q0's initial state, and you would have more than one choice to the next configurations. Then from that, you would also have more than one. So then it looks like a tree. If you look at all possible computations, it is a tree, and the height of the tree is T of length of X. So how do you determine whether this X is accepted? So you just look at a particular, whether there is one that's end up at accept state. So this is the final configuration, this accept state is there. So then if there is such thing, then you accept. So that means the rejection. Now this is the difficult part. Now how do I know, how do I reject one? Then you have to look at all possible paths, and none of them has a QA. Then you reject X. So that is exponential. So if you look at this, so in other words, this non-deterministic computation with a time-bound T has this following property. If you tell me, okay, so this is just, so this has a property easy to verify. Easy to verify. Oops. Once you are given an input X and you're given a path, I can verify whether that path you give to me is actually end up at QA. But then if you want to find such accepting paths, you have to look for one from this tree, so that's hard. So it's, so let me put a quote there because hard to find a solution. So this is easy to verify a solution, but hard to find. So that's non-deterministic within this time bound. Okay. So there are a lot of problems in practice when you change this T to polynomial P. That has this situation. So we are going to see some of those. So what we have been doing up to this point is to find deterministic algorithms. On Turing machine, even though our underlying machine or computation model is RAM, but we know that RAM and Turing machine, one Turing machine, they are equivalent in power within a polynomial. Okay, so that is our computation models. Let's go back to this slide. Okay, so now let's define two important classes. Now, these are decision problems. So what are decision problems? Decision problems just means you have a set of instances. So normally let L be a set of, so this usually we call it the positive instances. And then you are given any instance X, I want to know whether X is a positive or negative. So in other words, I want to know whether X is in L. So this is called decision problem. Okay, so let me give you an example. For instance, I can, which we're going to look at later, SATB, the set of all Boolean formula of Boolean formulas where this Boolean formula is satisfiable. Okay, so it is a decision problem. So in other words, you are, let's say I'm given a Boolean formula. I want to know whether this phi is satisfiable, meaning whether you can find a truth assignment to the variables contained in phi to evaluate this phi to be true. So that's satisfiable. Okay, so that's a decision problem. And of course, you know that it's easy to verify if you are given a truth assignment and you say that truth assignment makes it true, I can verify it. It's pretty easily. But finding that truth assignment is not easy. Okay, so we don't know. Nobody knows how to find it efficiently for any given Boolean formula because this SAT is NP complete. But here we just explain what a decision problem is. Okay, then we can define two important classes. One is deterministic Turing machine. The other one is non-deterministic Turing machine with polynomial time bound. Okay, so P is a set of all decision problems, D, where D is solvable by a deterministic Turing machine in polynomial time. And NP is the counterpart of P with non-deterministic Turing machine. Okay, so D is solvable by a non-deterministic Turing machine in polynomial time. As we said earlier, that problems in P are considered tractable or efficient. Okay, so we don't want to use that efficient because in practice, if it's a high degree polynomial, it's not efficient, but we just say it's tractable. And obviously, P is included in NP, okay? Because deterministic Turing machine is just a special case of a non-deterministic Turing machine. But then we want to know whether P is equal to NP, and nobody knows until now. Well, nobody knows since it was first raised in 1960. So that's 60 years almost, right? So 60 years after, we still don't know the answer. Even though a lot of people believe it is not equal, but either way, it's possible because there isn't any mathematical proof for it. So as a matter of fact, this is one of the 10 important problems in computer science that a company put money on it, right? So if you can solve this problem, you make $1 million. So I hope that price still holds true. Okay, so lots of people trying to do this. That's not our purpose, try to solve it. Our purpose is try to understand it. Okay, so why it is hard. Okay. All right. So let's move. Well, of course, if you can solve it, that would be great. Oh, Zoom doesn't. All right. Now, remember what we want to know is that we want to find out the hardest problems in NP. So we want to find out the hardest problem in NP in the sense that if you can solve one such problem, then every other problems in NP can be solved in polynomial time. Okay. So then we need to use some tools. Okay, so the tools here is called polynomial time reduction. We can reduce a problem to a different problem. Okay. So let's look at its definition here. We are defining a polynomial time reduction. So let me open up a whiteboard. Okay, so let's say I have two problems, A and B, and I want to compare which one is harder. So what I want to do here is that we are going to say, so we are going to say that A is reducible. A is polynomial time and many to one reducible. Sometimes people call many to one mapping. Reducible to B if the following is true. First, if there is a P time polynomial time, shorthand for that is P time, right? P time is shorthand for polynomial time. There is a P time Turing machine, call it DTM. And let me just say, sorry. There is a P time computable function, let's call it F. Okay, so which means that there is a deterministic Turing machine that computes F in polynomial time such that, okay, for all instance of A, if X is a positive instance, then F of X, now this is a mapping, is a positive instance of B and vice versa. Okay, so that is reduction, and this reduction is denoted by A less than or equal to M, B with a P on top. So P indicates a polynomial time, and M here indicates mapping or many to one. So if we want to look at a picture, it's just like this. So let's say I have A. So inside this is a positive instances. And I have B, so inside that is a positive instances. And then these positive instances under F will go to a positive instance. So this maybe go to the same one. The other may go to a different one. And the negative instances will go also to the negative instances. Okay, so that's a reduction. So now, once you have this, then we can have the following. So then we can compare which is easier. Let's go back to our slides here. Okay, so let's look at this proposition. Number one is, so number one says polynomial time reductions are closed for P, meaning if A is reducible to B in polynomial time, and then B is solvable in polynomial time, then A is solvable in polynomial time. So that means that A is not harder than B, right? So, or you can think of it as A is easier than B, okay? Because if B is solvable in polynomial time, then A is solvable in polynomial time. And this reduction transitive. If A is reducible to B, B reducible to C, then A is reducible to C. Okay, so the proof here is not hard, so you can find it in your textbook. So I'm going to skip the proof. Okay, now we are going to define the hardest problems in NP. Okay, so this is the definition. So let's say I have this NP. I think that someone's mic is on. You can hear some background noise there. So let NP be a set of decision problems that D is accepted by NTM in P time. So there are lots of problems. It includes P also. So what's the most difficult problem or the hardest problem from computational points of view? So of course, obviously, the one that any problem can be reduced to will be the hardest, right? So that's the concept of NP complete problems. Okay, so now let's look at this definition. A problem D is NP complete if first, D is in NP. Second, any other problems in NP is reducible to it. Then this D is the hardest because if D is solvable in polynomial time, then every problem in NP is solvable in polynomial time. So which means that P then is equal to NP, right? Okay, so that is this concept. Okay, so once we have this concept, then we want to know what kinds of problems are NP complete. So how can we prove a problem that in NP that is the hardest in NP? Okay, so first of all, I would like to mention here that there are thousands of problems that we have encountered in different fields that have been shown to be NP complete. Okay. Then here we are going to, so in our, in this video, we are only going to show 4 classic NP complete problems. Okay, so they are bounded halting, bounded tiling. So this is called Levin's theorem also, and bounded satisfiability, which is called Cope's theorem. And then this is a special case of 3 satisfiability, and that probably can be called Cobb's theorem, because that, so this is due to Levin. We're going to present a different version, and this is due to Cook, and this is due to Cobb. We have seen earlier when we look at maximum flow problem, we have is Edmonds Cobb algorithm, and then when we look at string matching, we have a Rabin Cobb. So that's that Cobb. Okay, so he has made a lot of contributions in this field. And both Cook and Cobb were awarded in different years, okay, Turing Award. Now, Turing Award was the, is right, the most prestigious award in computer science, sort of like a Nobel Prize kind of thing. So Levin should be given one, but then Levin was in Russia at that time, so he didn't get it. Okay, now he is at EU. Still teaching, and Cobb is at UC Berkeley. I'm not sure whether he's retired or not, and Cook is in Toronto. All right. I did my PhDs in average and in complexity theory, and I did a lot of work on average case NP completeness. So that's why I knew them very well. Okay. All right, but that was a long time ago. Now I didn't do these things anymore. Okay, so these are the 4 problems we're going to look at. I'll try to erase it. Couldn't. All right, so the first is the easiest one. It's a bounded halting. So we just want to know whether a time-bounded Turing machine halt on any given input X will halt in that time bound. So we first look at a general halting problem that is without time bound, and then we're going to just add a time bound to it. So this is a halting problem. The reason I use it is because I'm sure you have seen it. You have seen this halting problem in your previous course, Foundation, right? So it's an undergrad version of Foundation of Computer Science. So the halting problem is like this. So you have an encoding. So this thing represents encoding of a Turing machine, which once again, a Turing machine, so you can think of a Turing machine as a program. Okay, so on RAM, right? So, and then in Turing machine, we also have this concept called universal Turing machines. So which can take a Turing machine as an input and the input X to that Turing machine as input also, just like our computer, right? So you have a program, you load your program into the memory, you load the input to that program into the memory, right? Okay, so time is up, so I'm gonna stop here. Any questions for me?
Not so far.
Okay. All right, so we change direction, so which means that you may want to refresh your memory of Turing machines, right? Okay, so we're gonna use Turing machine quite a bit in this part of the materials. All right, so I'll see you on Wednesday.
Tuesday. There's no class on Wednesday,
Oh,
right?
that's right.
Tomorrow?
I'll see you tomorrow. Thank you. Thank you.
Thank you.
Yeah, see you tomorrow. Yeah.
Thanks.
Bye-bye.
Bye.
Yeah.